Hello dear learners. In today's lecture, we will talk about ionospheric conductivity. In the last class, we have seen what is the DC conductivity and how, starting from the simple momentum equation, we have obtained the conductivity expression. So, the DC conductivity was defined to be sigma DC is equal to NE square divided by me nu, right? So here, most importantly, we not considered the magnetic field, and the nu is the collisional frequency, and q is the charge, m is the mass of electron, and ne is the number of electrons per unit volume, right? So the idea of conductivity is how plasma, if it is diffusing in the presence of collisions, how the plasma's conductivity can be defined is actually the topic of discussion. So we have already made time varying terms to be 0, and we also neglected the pressure gradient force, and in this simple assumption we have obtained this expression. This expression also leads towards the mobility of electron. Mobility is the velocity per unit electric field, let us say UE by E, which will be QE divided by me nu. We also discussed the consequences of this expression in terms of how the mass of the diffusing species and the number of collisions it encounters will affect the mobility, right? Now, let us say now we introduce the magnetic field into this picture, and with the presence of magnetic field, how things will change. Or when you have a static magnetic field, it makes the plasma anisotropic. So, with the electric current flowing in the direction other than that of the applied electric field, requires the conductivity expression or conductivity term to be given as a tensor. So, we will actually derive what this conductivity tensor is. So, making the force balance simple. So, the Lorentz force QE NE times, so we are writing capital NE times E plus UE cross B will be approximately equal to ME NE nu UE. So here the Lorentz force, or the force due to the electric and magnetic field, is essentially compensated by the collisional term, and from this we can write the conductivity J is, as we remember, NE VD, or in terms of the variable that we have defined for this purpose, we write it as QE NE times UE. So this can be written as NE QE square divided by me nu times E plus UE cross B. Right. Which is the simplified form of the generalized Ohm's law. Let us say we call this equation as equation number 1. Now, we know that in terms of the electric field and the conductivity, we have this expression J is equals to sigma dot E. So, sigma is the conductivity. So, earlier we are calling it as the DC conductivity. So, we can write this expression, let us say, from the first part of the left hand side of equation number 1, we can write, so equation 1 leads to the velocity being identified as J by NE QE. We already have this electric field, we have substituted for magnetic field and find out how J will look like and what and all will constitute for the sigma if this expression has to be valid. Okay. So, with velocity is written like this. So, J, the conductivity, can be written as, so this is the DC conductivity, we already have this here, right. So, this is the sigma DC. So, we can write it as sigma DC times E plus velocity is J by NE QE cross Now we have to worry about this J cross B term, right? Now let us define the magnetic field in such a way that B is equals to, the magnitude is B naught and the direction is along Z cap. So we have to use this into this expression, calculate or evaluate the curl, and then find out the components of the conductivity. Okay. So we will use this expression, and to the total conductivity, J is equals to sigma dc times the electric field plus times B naught divided by NEQE times J cross B. So this can be written as B is B naught. No, I have already written B naught, so it should be Z cap. So J in its vector form can be written as Jx x cap plus Jy y cap plus Jz k cap, and Z cap is vectorially 0 0 or 1 Z cap, right? So the curl will look like, so J cross B naught or J cross Z cap will look like Jx Jy Jz cross Z cap. So we can do this I cap, J cap, K cap, Jx, Jy, Jz, 0 0 1. So effectively we also know that x cap cross Z cap is minus y cap cross Z cap is x cap, and Z cap cross Z cap is 0. So effectively we can write this curl as minus x Jy plus y cap Jx. So this is what I am talking about, right? So substituting back into the original equation, we can write J as sigma dc times the electric field. The DC conductivity part is remaining as it is, plus sigma dc times B naught divided by QE NE times x cap Jy minus y cap Jx. Convenience, I am using the same notation. So it is x cap times Jy minus 0 minus y cap. Yeah, this could have been x cap Jy minus y cap Jx minus y cap Jx 0. Right. So this is J, the conductivity in terms of both using the magnetic field and electric field. Right. Now where do we go from here? So here we may have to look at the equation like a vector equation and write the different components of the conductivity equation or the conductivity tensor. So this equation is actually a single equation, but let us try to understand what is the physical or what is the inference of this equation. So the total conductivity is made up of this DC component and another component which is basically dependent on the magnetic field. And more importantly, there is no component which is aligned along the Z cap, because B naught, Z cap is the direction of magnetic field. So you see this Z cap along Z cap, there is nothing. That means the parallel component of magnetic field will vanish. So what I will do is I will just separate this equation into the three components. So Jx is equals to sigma dc Ex. So we should also identify the electric field E as this vector Ex, Ey, Ez. So this is a vector equation and these are the scalar components. Sigma dc Ex plus omega Ce by nu, the collisional frequency, times Jy. I am extracting only the components which are along x cap. So I don't have to write component or the unit vector x cap here because I am just looking at whatever that is present along the x cap direction. So omega is qb by m. Omega is the frequency, the gyration frequency, which is qb by m. Okay, and jy, the y component of the conductivity, will become sigma dc times Ey minus omega Ce divided by the collisional frequency times Jx, because I am now referring to this term along y cap, Jx. And the current density along the z direction is only the dc component, which is along the same direction. Right. Now let us say we call this equation, the original equation, as 1, of course, and then probably this as 2, and then this after breaking the curl, this as 3, and this is 4a, 4b, and 4c. Right. So let us just quickly look back to what we have done. So we have just taken the equation from the DC conductivity, which is defined like this, and removing all the time variation and writing the magnetic field to be along the z cap direction. We have got equation number 1, and in this term, here is the velocity. You have the conductivity appearing on the left hand side, for which the entire equation is written, right? But on the right hand side, you have the velocity. So from this simple formula of J is equals to NEVD, we have written the velocity again in terms of the conductivity, right? So this is J. Now, the components, of course, it will come later, but here, now that you have written the velocity in terms of conductivity, now you are evaluating this curl between the J and B. Taken J to be present along all the three directions and the magnetic field only along the Z direction, you evaluate this curl and substitute back into this equation. Right. Now, this conductivity now seems to be an addition or a sum of these two terms. One term which is entirely based on the electric field or the DC conductivity. The second term is based on the magnetic field. And if you split this equation number 3 into 3 component equations, this is what you get. These are very important or very fundamental equations in understanding the ionospheric conductivity. Right. Now, let us take these equations and try to find out the tensor nature of the conductivity. I'll rewrite these equations in terms of variables or parameters that I know very well. So let us take equation number 4a, which is Jx conductivity along the x direction. Jx is equals to sigma dc along Ex plus omega Ce divided by nu times Jy. If you look at this equation, maybe I should go back. If you look at this equation, Jx, the conductivity, these are the components, right? So there is no point of writing them as vectors. So Jx is conductivity component along the x direction. Now, it seems to be dependent on jy, right? And jy along the y direction seems to be dependent on jx, right? So, what I am going to do is, I will substitute jy from 4b into 4a, and then I will eliminate jy from this expression. So, then I will have jx entirely written in terms of jx itself. Then I can separate them, or I can extract them and find out an expression. This is where I am going to make a simple substitution. So, here it will be written as sigma dc times ex plus omega ce divided by nu. For jy, I am going to substitute, use equation 4b. Okay, so which will be sigma dc ey minus omega ce divided by nu times jx. Right. This seems to be a more logical equation, in which, of course, there is electric field components Ex and Ey are now present, but still the entire equation has only, I'll simplify it even further. So, it can be written as sigma dc times Ex plus omega ce divided by the collisional frequency, sigma dc Ey minus omega ce square divided by nu square times jx. Nu is the collisional frequency. So, I will extract jx to the left side, and I write jx times 1 plus omega ce square divided by nu square is equals to sigma dc times Ex plus omega ce divided by nu sigma dc times Ey. Or further algebraic simplification, nu square plus omega ce square divided by nu square is equals to sigma dc times Ex okay. Now we write jx is equals to nu square divided by nu square plus omega ce square to sigma dc times Ex plus omega c. Yeah. Nu will get cancelled from the denominator, sigma dc into Ey. Right. So, this is just jx. So, one value of the conductivity, right. So, similarly, what I have done in this case is just substitute 4b into 4a, so that I have only jx. So, similarly, I can also substitute 4a into 4b, so that I get an expression for jy. So, if I do that, similar algebra will lead me to jy is equals to minus nu omega ce times sigma dc into Ex divided by nu square plus omega ce square plus nu square by nu square plus omega ce square sigma dc Ey, which is actually a similar looking expression if you compare. And Jz, which doesn't depend on the magnetic field, will simply be having the DC conductivity component along the respective direction, right. So, these two equations. So, let us write these three equations in a single place because they are very important for understanding the conductivity. So, Jx is equals to nu square divided by omega c E square plus nu square times sigma dc times Ex plus nu omega c E divided by nu square plus omega c E square sigma dc into Ey. Jy is equals to minus nu omega c E So, I am just writing them in such a way that the electric field components can also be matched. So, nu square divided by omega c E square plus nu square times sigma dc Ey and Jz is equals to sigma dc times Ez. Right. So, most importantly, the conductivity along the Z component is just a humble component which just depends on the Ez, right. Now, look at this equation, you observe these terms, the collisional frequency and the gyration frequency, how they are depending on the electric field component along the perpendicular direction, right. So, Jx has this Ex, Ey, Jy also has Ex and Ey. Similarly, Jz has Ez, right. Now, from this equation, we can write this in a matrix form and see the tensor nature of the electric conductivity. Okay. So, in this lecture, what we have done is simply starting with the DC conductivity expression, we have defined the mobility, which of course just a consequence of how the collisional frequency and the mass can affect the mobility in a diffusive equilibrium situation. So, from the earlier class itself, we have established this balance of the collisional force and the electromagnetic force acting on the particles. If these two forces are of course compensated, then what you get is this simple expression which is equivalent to the Ohm's law, J is equals to sigma E. So, I have this expression which is written in terms of the DC conductivity, but then you have added the magnetic field. The velocity written in terms of the current density gave J vector on the right hand side. It calculated the curl of J with respect to the direction of magnetic field, which has given these three equations. We realize these equations are coupled in the sense one component of conductivity has dependence on the other component of the conductivity, vice versa. We realized by simple substitution we can remove this dependency and obtain valid equations for the conductivity Jx, Jy and Jz. So, in the next lecture we will try to write this in a matrix form and understand what is the meaning of the conductivity along different directions. So, now the point is, because of the presence of electric field, the magnetic field, the conductivity is different in different directions, right? Because the magnetic field creates anisotropy in the plasma. Okay, so we will try to understand more important aspects about this conductivity in the next lecture.